Okay, 2012 number 4. This is a great problem, I think. It's got a lot of stuff in it. This would be hard to categorize into one of my 6 categories because it really has a little bit of a lot of different things in it. And for that reason, I like it. But the report from my students last year was they really liked this problem. They felt like they did very well on it. So we've got a function. We've got some values here. This is no calculator. Don't be scared by those decimals. It's twice differentiable, so it just means we can find derivatives. We know that f of 1 is 15 and f double prime of 1 is 20. The values of f prime, the derivative of f, right, so I have values of the derivative here, are given for selected values of x in the table above. So first, part A, write an equation for the tangent line to the graph of f at 1 and use the line to approximate f of 1.4. All right. So let's see. We have the tangent line. We need a point. The point at x equals 1, the point is 1 comma 15. And the slope is f prime of 1, which is 8. So that would give me y minus 15 equals 8 times x minus 1. And since I'm going to actually use it, I'm going to write it in slope-intercept form. That would be 8x minus 8, and then plus the 15 would be plus 7. All right? So there's my line. And then plugging in would say f of 1.4 is approximately equal to what you get when you plug 1.4 into this line. That's 8 times 1.4 plus 7. 8 times 1.4 is, that gives you 8, and the 0.4 times 8 is 3.2, so that's 11.2 plus 7, which is 18.2. Okay? B. Use a midpoint Riemann sum with 2 subintervals of equal length. That would be 2 subintervals of equal length, and here are the midpoints, to approximate this. Okay, let's go ahead and do that. So the area from 1 to 1.4 under f prime of x dx would approximately be equal to the area of these 2 rectangles. This rectangle is 0.2 wide times 10 high, I'm using the midpoint value, plus this rectangle is 0.2 high times the midpoint is 13. So that gives me 0.2 times 10, that's 2, plus 0.2, 2 times 13 is 26, so 0.2 times 13 is 2.6. That gives me 4.6. Now they want us to use the approximation to estimate the value of f of 1.4. Well, that's a little fundamental theorem of calculus. This, of course, we know the antiderivative of this integral, or this expression, that's just f of x from 1 to 1.4, because the antiderivative of the derivative. So that would be f of 1.4 minus f of 1. And then I found a value here, that's 4.6, right? So f of 1, well, we know that, they gave us that, that's 15. So fundamental theorem tells us that this is all true, and then I can just add this to the other side. So 4.6 plus 15 is 19.6. And notice that our approximations are, like, you know, close-ish. They should be. All right. Isn't this cool? C. Use Euler's method, starting at x equals 1, with 2 steps of equal size to approximate 1.4. Cool. Another way to approximate it. So I've got x, y, dy dx, and delta x, and I multiply those together, and that gives me delta y. right? Those are the columns in my little Euler's method table. And if you want like this times that equals that, right? Because those are approximately equal. So I'm starting at 1, which is the point 1 comma 15, and 2 steps of equal size to get to 1.4. So that means I'm going 1.2, 1.4, and that means my delta x is I'm always going up by 0.2. Well, what's the slope here? What's dy dx when x equals 1? It's 8. So 8 times 0.2, 8 times 2 is 16, so that would be 1.6. And adding that over to this, that gives me 16.6. Right? And then I go over, I need dy dx here, that's 12, right, from the table. The derivative at 1.2 is 12. And 12 times 2 is 24, so that would be 2.4. And then 2.4 added to this is 19. 19.0 if you want. 19.0. Again, it's close to these approximations. It should be. Cool. What other ways can we approximate it? How about by writing a second-degree Taylor polynomial for f at x equals 1, and then use the Taylor polynomial to approximate f of 1.4? What a great idea. Well, second-degree Taylor polynomial, I'll just call it t with a 2 to second degree, that's equal to, it's at x equals 1, so it's f of 1 plus f prime of 1 times x minus 1 plus f double prime of 1 times x minus 1 squared over 2 factorial. Right? This is the recipe for how to build one, and you certainly need to know that. So if you didn't get that far, I would certainly pause it here and then try to finish this from there. But I'm going to do it right now because I think this problem is so awesome. I can't wait. So the second degree Taylor polynomial is f of 1, which is 15, plus f prime of 1, which is 8, times x minus 1. And notice, if you just stop there, you get the tangent line, right? Because, of course, the first degree Taylor polynomial is the tangent line. First degree is linear, right? So notice that those are the same so far. And now we're going to put in the quadratic term, too. And the second derivative at 1, it's not in the table. But hey, remember they gave us that here? That's 20 times x minus 2, x minus 1, excuse me, squared over 2. 2 factorial. It's just 2. There it is. And now we want to use that to approximate 1.4. So the second degree Taylor polynomial at 1.4 is 15 plus 8 times 0.4, 1.4 minus 1, right? Plus 20 divided by 2 is 10 times 0.4 squared. So that's 15 plus 8 times 4 is 32, so that's 3.2. 0.4, well, 4 squared is 16, and 2 decimal places, that means it's 0.16 times 10 is 1.6. I know maybe you think that that's just horrible and unfair that they made you do that without a calculator, but you should be able to do that. This is 15 plus 3 is 18, 19.8. So there's our 4 approximations. What an awesome problem.